Hi everyone, welcome back for week 7. We'll get going in just a couple minutes time. Make sure you got everything you need with you. Something to drink as well. Morning Josh, good to see you. Morning Healy, welcome back. Okay, welcome back for week 7, guys. I hope we're all healthy and well. I'm going to go ahead and turn my camera off now. Don't need that anymore. So, we're looking at trigonometry this week. This is a very big topic. This, along with differentiation, are probably the two biggest topics in Year 12 maths. So, it's going to be a challenge to try and fit it into the 2 hours we normally allocate, but we'll see how far we get and go from there. So as always, we're going to look at the rules and basic applications and how they apply, how we take the rules and apply them. Use the live chat, our emails and our phone numbers to get in touch with us either during the lecture or afterwards if you've got any questions and you want help with anything as well. Pause the video if need be. More problems are in the description, and as always, feedback is welcome. So, this is just an overview of what we're going to look at. There's only 4 bullet points here, but within each of these, there's quite a lot, particularly around solving trigonometric equations and the different ways that these rules and the area formulae can be used. It's really important that we have a solid understanding of algebra, how to rearrange equations, how to make different things a subject before we look at trigonometry. So, first thing is, let's just have a go ahead, some retrieval practice. Write down the sine rule, cosine rule, and the equation for area of a triangle. I'm giving you a triangle here if you want to use this notation here. So I'll give you about another 20 seconds and then I'll reveal them so we can check. Okay, so on the left hand side here, we've got the 2 versions of the sine rule. If you've only got one, it doesn't matter. They're just reciprocals of each other. The key thing is that you've either got all the angles on the numerator and all the sides on the denominator, or the other way around. But as long as you're consistent, it doesn't matter. Then over here on the top right, we've got our cosine rule for working out a side. And then again, we can just rearrange this if we want to work out the angle. The way I always do this is I just remember this formulae and I commit this to memory. I write it out and then rearrange if I need be, rather than trying to remember 2 versions of it. So I'll just remember one version and then rearrange as appropriate, taking care of this negative when we rearrange. And then lastly, the area of a triangle. Some things I want to highlight as well. The notation here that we've got corresponding sides and angles labelled as the same letter, just different cases. when we are dealing with the area equation, this angle here must be between these two sides. So we've said AB sine C here, we could have AC sine B or CB sine A, it doesn't matter as long as the angle is between the two sides. And similarly with the cosine rule, this angle, so this side must correspond to this angle the cos is being applied to. Okay, we can't have different letters here. This side and this angle must correspond to each other. Okay, but we've got to make sure we commit these to memory as well. So, some quick questions here just to get us, we may not have done this and practiced this for a while, so some very quick questions here just to get us back into the right way of thinking. So each time we're just working out the missing letter. So in this case we've got beta down here, we've got the side x here, and then angle theta for this last one over here. And I'll give you about a few minutes to have a go through those. I'm just going to write these answers up as well. Not the full solutions, just the answers. And then I will go through the solutions in just a moment. These are unrounded. So I'm just going to start working through this first question. These questions are fairly straightforward, so I don't want to spend too much time on them. I want to get onto some of the more challenging stuff that is more likely to come up in your exams. But it's really important we understand this as well. So what I would say is, if you feel like you need more practice on this bit, pause the video now, have a look at these questions, and then you can catch up afterwards. So this first one is going to be the sine rule. And then again, we'll just rearrange here to make sine beta the subject and then beta the subject by doing sine inverse, and we get our answer of 50.41 degrees. The other thing I'd always do is label up your diagrams. Just so it's really clear. Hopefully this last diagram's got some labels already for the angles, so we can just use that to go ahead and label up the sides. But if the labels aren't there, definitely go through and put them in. So this second question here, we can see we would use the cosine rule. We've got a corresponding side and angle here. The side is unknown. We've got two other sides that are known. So we would go ahead and use the cosine rule. So the first thing is always try and get, especially with the cosine rule, it's a bit more complicated. So before I do any substitution, I just write out the formula as it is originally, and then I'll go through and start substituting in my values. And then it's a matter of going through, working that out and simplifying to get this 12.808 value here. And then finally, this last one is again the cosine rule. We've got three sides and we're trying to work out the angle. So this is just taking this here and then rearranging it to make angle A the subject. So just to make sure, when we rearrange that, I'm just going to do it down here. When we rearrange the cosine rule to find an angle, what we should get is, I'm going to write it as cos A. Cos A is equal to A squared minus B squared minus C squared over minus 2BC. And then we would do cos inverse to find A. Okay? But always write this out first and then go ahead and rearrange it if need be. So like I said, if you want to practice these questions for a bit longer, pause the video, you can catch up in a moment, or come back to it at the end of the lesson. But trigonometry is a big topic, so we're going to have to push on a little bit today just to get on some of these other questions. Again here, these are some more practice questions, and I've put the answers on the side, just so you know if you're on the right lines or not. And again, what I'd say is, if you want to practice some more of this, take a picture or pause the video and have a go at them before coming on to the harder stuff. But we're going to go ahead and look at a slightly more complex applications of these rules and equations that we've just discussed. So there's a question up here. I'll give you some time just to read through that. So again, we've already got the angles labelled up, so first thing we want to do is go ahead and label up the sides here. And then we can see and so parts A and B to this question are fairly similar to the questions we've just done, so I'll give you some time to work through those, and I'll just write up the answers we should get for them. So I'll give you about another minute or so to finish answering parts A and B there. And if you want to go on part C, you're more than welcome to. That's where I'm going to focus the explanation for this question. So you can wait as well. Okay, so I'm just going to start working through part C now. Again, if you're not onto this part yet, feel free to just pause until you get up to there. They've given us additional information in part C, and it's really important whenever you have a diagram and there's additional information given to it that isn't already in the diagram, it's really important that you put it onto the diagram. Okay, it makes it much easier to focus and pick out the relevant bits of information. So we can draw this point D in here, and we know it has to be somewhere there because this is an acute angle. If we did it directly down, it would be perpendicular. If we did it to this side, it would be obtuse and be bigger than 90. So it has to be towards this kind of area because it's an acute angle. We also know that we can call this point D here, and that this has angle 63 degrees. And we are being asked to work out the length of BD. And so actually what I would do is now draw out this triangle ABD separately so that I can ignore all the information that I don't need. And then we're being asked to work out this length here, BD. So now we should see that actually this is now significantly more straightforward question than it initially looks like when it's worded like this. So again, I'll give you some time just to go through and have a go at finishing this question. And the answer we should get is 6.49. Oh, sorry. 6.49 centimeters. We can see here we've got corresponding angles and sides, and then another pair of corresponding angles and sides. So we're going to need the sine rule to work out that length of BD there. So just to recap some of the key bits in this question, is always add information to a diagram. And then when you've got bits of information that you're trying to ignore on a diagram, for example, the 17 and point C here are irrelevant, this side here are now irrelevant, draw it out onto another diagram because it makes it much easier to focus on and see what you need to do when you haven't got extra information that you're worried about. Okay, so let's go on to another question. I'm just gonna zoom in on this a little. Give you some time to read through the question here. So again, think about what we did last question in terms of adding information or drawing out new diagrams. Think about if that might be relevant here. And I'm just going to write up the answers in case you get to that point. These answers haven't been rounded, so you may get slightly different ones if you rounded them. So for parts A and B, I would just draw out this triangle ABD here. We can ignore point C for now because we don't need it. And then for part C, we don't need point D for part C, so I would again draw out the triangle. This one, draw out triangle ABC. And again, just writing on the lengths or information that we're trying to find. And then we can again see that hopefully now we've drawn them out into separate diagrams, it makes it a lot more straightforward to see what we're dealing with and what we're being asked to find. So I'll give you just a few more minutes to finish off anything you need to finish off. Okay, so sine rule, cosine rule, and area of a triangle are also in the GCSE spec. And and a lot of these questions go slightly beyond the GCSE spec, but this should be information that you hopefully will have come across before year 12. So I want to push on and look at some stuff that is specific to year 12, which is now what we're going to focus on for the remainder of the session. So first thing is, again, some retrieval practice. Have I got writing down the trigonometric identities that you have learnt so far? So there should be 2 of them. And we should get in no particular order. So we've got sine theta over cos theta is equal to tan theta. And the second one is sine squared theta plus cos squared theta is equal to 1. Okay, and we can look at proofs of these and you can look them up. We're not going to go through them today. You won't be asked to demonstrate a proof of them in your spec, but sometimes it's interesting to know, so you can definitely look them up. There's definitely some brilliant videos out there on that. Just a few things to add is, if we had, for example, on the right hand side, if you had 4 sine squared theta plus 4 cos squared theta, this would also equal 4, right? So we can just multiply through and change the coefficients as appropriate, as long as it's kept consistent. Okay, so what we now get is a lot of these kind of questions saying prove that this equals that, and what we want to do in a prove that question is generally keep one side the same. So in this case, I would keep cos squared x the same and manipulate the other side. And the reason in this question I'm saying let's keep cos squared x the same is because it's easier to always put things in terms of sine and cos and not tan. So we can get rid of tan quite quickly here and do that. So the 2 principles generally are always try and get into sine and cos where appropriate, and always change one side at a time. That may not always work. Proving trigonometric identities is just about having a go and seeing where you get to. Okay, so I'm going to use some time just to have a go at this question here, and I'll reveal the second one as well, just in case you get onto it. So I'll give that another 20 or 30 seconds. And then I'll go through question 1. So question 1, like I said, I would keep the right hand side the same. The left hand side, the first thing I'm going to do is get rid of this tan x and change it into sine x over cos x. And then we get this times sine x times cos x. And we can see here then this cos x will cancel with that cos x. We've got sine times sine, so this will give us 1 minus sine squared x. And we know from the identity that this is equal to cos squared x. So we can say therefore we get cos squared x is identical to cos squared x, and this has been proven. So similarly, I'll give you some time to go for question 2, about another minute, and then I will go through and answer that one. And if you've done question 2, there's one more down here to have a go at as well. Okay, so we know that tan x is equal to sine over cos. So we can say, well, therefore, 1 over tan x, if we take the reciprocal of the left-hand side of this identity, we can also take the reciprocal of the right-hand side, and we're going to get 1 over tan x is equal to cos over sine. So now, again, I'm going to keep the right-hand side the same. I can write the left-hand side as sine x over cos x plus cos x over sine x. And in order to add these fractions, obviously we need a common denominator, which means we're going to have to cross multiply. So I'm going to have to multiply this fraction here by sine x and this fraction here by cos x. So actually what we end up with is sine, this is going to equal sine squared x plus cos squared x over sine x cos x. And again, we use our identity, the other identity. This is 1. Sine squared plus cos squared is 1. So we get 1 over sine x cos x is identical to 1 over sine x cos x. And we've got left hand side is equal to the right hand side. Okay. And the last one, question 3, is a bit more straightforward in my opinion than questions 1 or 2. So I'll give you just a couple minutes to, no, about half a minute to go through that one, and then I'll go through the answer as well. So as always, if you haven't finished question 3, just go ahead and pause the video. But for now, I'm going to go through this answer. So we know that sine squared plus cos squared, let's put the theta in there, is equal to 1. And we said earlier we can multiply and change the coefficients as long as we stay consistent throughout the identity. So we can get 5 sine squared theta plus 5 cos squared theta is equal to 5. And then if we rearrange this, we do minus 5 sine squared theta from each side, we can see we get 5 cos squared theta is equal to 5 minus 5 sine squared theta. So actually this up here is just equal to 5 cos squared theta. And that's our answer there. Okay. So I'll give you a moment just to get the copied out. And again, just a reminder that always what we're looking to do is when we're proving identities, keep one side the same and manipulate the other side so that we get it into the format that is shown, and we show that left hand side and right hand side are equal. Generally, emphasis on the generally here, generally we want to simplify everything down into sine and cos. So if we have tans, we want to get rid of them like we've done here. Always, whenever you're doing a prove that question for your identities, I'd say write out your identities on the side of the page, just so you have them to refer to and you don't have to keep recalling them. Okay, so let's have a go on to the next bit. Again, as always, we've got an exam question here, so I'll give you time to read through and answer this question before I show you the solution. So I'll give you about another half a minute or so, and then I'll start writing up the solution for this question. Okay. So first thing we want to do here is we've got two pairs of brackets, both of which that are squared. So we want to expand these brackets. So first, let's just write these brackets out, get rid of the squared symbol and write them out repeated. So like this. You don't have to do this step, but it just makes it a bit easier when explaining what we're doing. So we've got this now written out. We can go through and expand this bracket and multiply these brackets out now. So we're going to get So the one thing I want to draw your attention to is these two terms here. is that I've combined these. So I've done, for example, 3 sine x times cos x plus cos x times 3 sine x. So I've done there's two multiplications that I've done to get these middle terms here. So I just combine those. But you can also see that actually I've got plus 6 sine x cos x and minus 6 sine x cos x. So they're going to cancel out with each other. And then I'm just going to try and group like terms. So we've got 9 sine squared x. I'm going to put plus 9 cos squared x. Plus cos squared x plus sine squared x. And then simplify this, we get 10 sine squared x plus 10 cos squared x. And like we said, sine squared x plus cos squared x equals 1. And then we can just multiply through and have some coefficients there as long as we keep it consistent. So this is just going to equal 10. Okay, so I'll just give you a moment to get that copied out. And then we'll move on to the next bit. Okay, so next question. We're going to go on to look at the trigonometric graphs. So first thing is, again, some retrieval. Make sure we know what the graphs look like. We're going to go from minus 360 to 360 for each of these. And then let's do the graph of sine x here, cos x here, and tan x at the end. So have a go at drawing out those graphs and sketching them out. And I will draw up the full diagrams in just a moment. So what I would always do when I'm drawing out trigonometric graphs is draw out the graphs first and add the values in later. Just because it makes it a bit easier when you're drawing it freehand. We're not worried about 100% precise sketches at the moment. So for sine x, we've got to start at 0 and draw a wave in here, and then we're just going to mirror that and translate it back as well. And then we're going to mark on our key points. So we've got 0 here, this is 180, this is 360, then we've got minus 180 and minus 360 here, and it goes from minus 1 up to 1. Minus 1 up to 1. And our maximums occur at halfway between these values. So minus 270, minus 90, and then plus 90, positive 90 and positive 270 as well. Cos x has a line of symmetry about the y-axis. So if we draw this first bit from 0 to 360 here, so again we've got 0, we've got 180 here, we've got 360 here, and again this goes from minus 1 up to 1. And then we just mirror that in the y-axis. And we're going to get minus 180 and minus 360 there. And then finally, we've got tan x, and tan x is slightly more complicated. So we're going to start at 0 and go up like this, and then we're going to draw an asymptote here. This is at 90 degrees. Then we're going to go, I'm going to go back up again, draw another asymptote at 270 degrees, and then we're just going to draw this down here at 360 degrees. And tan it goes up to infinity and down to negative infinity, so we don't need to mark on anything. Let me just make that clear. You don't need to mark on anything on the y-axis for tan. And you can see tan repeats every 180 degrees. So we can just take this, oh, that is terrible. So we can just take this back here. We've got minus 360. This middle line is a little bit off, so I'm just going to redraw that. It should cross the axis about halfway through. There we go, that's much better. So minus 180 there, and 0 here. And then we've got minus 90 degrees here. And we've got 180 degrees here. Okay. And we can use these graphs and the symmetry rules to work out values of theta. What I mean by that is like this, for example. Let's say I want to find an angle for sine, and when I take the sine of that angle, I get an answer of 0.62. So 0.62 is going to be somewhere here. If I draw a line going through my sine graph, I can see I get two values. The calculator will give us always this first value here, the acute value. So now we need to use this graph to work out what this second value here would be. And this is where we get our rules of symmetry. So I'm just going to reveal them through our rules here. So this is for sine. And we can see here, let's say if I've got some value here of sine theta, I've got a theta value here, the value here would be 180 degrees minus theta. And the reason for that is the gap between here and here is going to be the same there and there, right? So this gap here is going to be the same as this gap here. Okay, so hopefully I think we are back online now. It looks to be working, so if there are any issues again, please bear with. We will get them sorted as soon as we can. So I'll just recap what we had here. We said that sine theta gives us, we can use sine theta to get different values that will give us the same output here. And we can also use that in the negative version as well. So we could take the same value that we've got here. So let's say this was, we made it up 0.62, and we wanted to find minus 0.62. We could use the same idea. So we take this line across, and the values that we get here and here are going to be exactly the same as these values here and here. They'll just be negatives. Right, they'll just be negatives. Okay? So, that's for sine x. I'll give you a moment just to get that copied out, and then we'll go through the graph of cos x. So our YouTube does seem to be working, the stream does seem to be working okay for now. If you have got any issues, just try pausing the video, refreshing it and coming back to it. Hopefully that should work. But it looks to be running smooth for now. So we'll go through these graphs and then we'll have a short 10-15 minute break before we come back. So cos x, I'll just reveal the rules down here for cos x. Cos x is a lot more straightforward. If we wanted to find this theta here, let's say again, let's take 0.62. We can see that we've got two values for cos x, positive at cos x, and two values for negative cos x. Actually, they're going to be the exact same, just with changing signs. So we could have, let's say this was, for example, 75 degrees. This might, down here might be minus 75. And the way we then work out this angle here is to do 360, subtract 75. Again, we're using the idea of gaps. The gap between 0 and 75 here is going to be the same as the gap between 360 and this value here. Okay? So I'm going to give you a few seconds to get the copied out and then we'll go through tan. And lastly, tan, a lot more straightforward. Like I said, tan just repeats every 180 degrees. So if we've got a value for tan, we just add or subtract 180 degrees depending on the range that we've been given. Okay, but it's really, really crucial and important we understand how to use these graphs and what we can do with them, especially when it comes to solving trigonometric equations. So let's just go through a simple example for tan. We can see, let me change that color. We can see here that if I had a value here, it would just be 180 plus 180 to get to that value there, minus 180 to get to that value there, minus another 180 to get this value here. The tan is significantly more straightforward than any of the other graphs that we work with. So, one last bit then is just a quick match-up exercise here. We've got various different angles and functions here, and I'll give you 2 or 3 minutes just to go through it and match these up as to what ones would match. So, for example, it's not on here. I'm just gonna give you one. We could have sine 72 degrees would be equal to sine of 180 minus 72 degrees, which would be sine of 108 degrees. So this and this would give us equal outputs. I'll give you again like a couple minutes just to go through that, and then we'll have a quick break before we move on to next bit of this. Feel free to refer back to the symmetry rules we looked at on the previous slide, but if you can, try and think of it without those, just to get some retrieval practice in as well. So about another minute and then I'll go through these answers. Okay, so I'm going to colour in, hopefully this works, I'm going to colour in the matching functions here. So we've got the first two done just there. And then we've got one that goes across different functions, this last one here to finish. Sine 180 and cos of 270 are both 0, so we can match those up as well. Okay, so we've been going for about an hour now. Really nice time to have a quick break, get some water, get a quick snack if you need to, and then when we come back we're going to look at solving equations. So let's say back at 12:15, and I will see you guys then. back. We'll get going in just about a minute's time. Okay, welcome back, guys. So now we're going to look at solving trigonometric equations, and this is bringing together all the different bits that we've just looked at in terms of identities, in terms of using the graph, in terms of rearranging formulae, and putting them all into one bit. So we're just going to start off very straightforward. I'm going to give you a second just to copy this question out here. These are the steps that we're going to use. Just so you can see that. So these are steps that we use. Step 1, I'll come on into and I'll explain these all in a moment. But for now, I'll just give you some time to get all of that copied out. Okay. So step 1, adjust the range only if necessary. What we mean by this, and we'll look at some examples of this. What we mean by this is when our trigonometric function is being applied to, the angle that our trigonometric function is being applied to, does not match the angle given in the range. So here, x and x match. But if this question was instead written as sine 2x is equal to 0.8, 2x and x don't match. So in this situation, we would adjust the range. Okay, but we're going to come into those types of questions a bit later on. For now, we're just going to keep it very straightforward, as we always do, is go through the basics first and then scale it up gradually. So we're going to go straight to step 2 and calculate the first value. And we say, well, if sine x is equal to 0.8, then x is going to equal sine inverse of 0.8. And we get our value of 53.13 ... and so on and so on. This is called our principal value or primary value. It doesn't really matter, but we can call it our first value. Right, our first value. And then what we want to do is use the rules of symmetry to work out the other values that would give us an answer of 0.8 if we applied the sine function to them. This time our range is from minus 360 to 360. So we're going to just draw our graph in here. And we've got our first value. This is positive 0.8 up here. We've got our first value here, our acute angle here, 53.13. So we can see that we'll get another answer here, which will be 180 minus that answer. And this is 126.8 ... And then we now need to look at how we're going to work out the two values in the negative part. In the negative part of our sine graph. So if we take this line back and we go down here and we've got another value here. So again, we're going to use this idea of symmetry and understand that the gap between here and here, 0 and 53, is going to be the same as the gap between these 2 points here. And we understand that this point here is minus 180 degrees. So this value here we will obtain by doing minus 180 subtract this 53.13. So we get an answer of minus 233.13 ... And again, we can round later. And then our final value here, again, we can use the idea of the gaps being symmetrical here. The gap from here to here is 126 ... So the gap from here to here is also going to be 126 ... And again, we can do minus 180 subtract that value. And we're going to get an answer of minus 306.86 ... And we'll round that to an appropriate value. So you can see doing this question without drawing the graph is very, very difficult. Very, very difficult. So it's really important that we draw the graph and we understand how this symmetry applies here. You can see I've drawn my arrows here and here and here and here. And we can then use that symmetry to work out these other values. Okay, so I'm just going to reveal the next two questions here. So have a go at doing these ones then for, so we've got a tan and a cos here. And I'll give you some time to go through and do that before I write up the answers for that. So I'm just going to start writing up some solutions for question number 2. Like I said, tan is slightly more straightforward. And all we need to do is add or subtract 180 degrees. It's really important when you're doing these secondary calculations that you use the unrounded value you found to start off with in that principal value. If we use a rounded value, then these are going to be slightly off in some cases, and that will skew our results. So it's really important that we use unrounded values here. Okay, so those are the answers for question 2. Question 3, let's do that up here. So we've got these first two answers using the rules of symmetry for the cos graph. So we had values here and here. And then, like I said, cos graph is symmetrical about the y-axis. So our negative values here and here are just going to be the negatives of these two values we've already worked out here. Right, going to be negatives of those two values that we've already worked out there. So actually we can just say that these are going to be plus or minus for both of these two values here. Okay. So hopefully you can see, as always, it's really important that we draw out the graph so we can see these rules and see how they work. Okay, so I'll give you a few seconds, a few moments just to make any changes that you need to make, get anything you need to get copied out, and then we'll go on to some more complex examples, still solving trigonometric equations, but just adding different layers and elements to these questions as well. Okay, so let's have a look at some other questions here. So again, it's the same as before. In fact, just for the sake of ease, we're going to cut this down and make this 0. So let's do the range between 0 and 360. And I'll give you a second just to get question 1 copied out there. So this is very similar to last time. The only difference is we can't find the angle straight away because we've got 4 sine x. So clearly we need to get rid of the 4 first before we go ahead and find out. So we would get sine x equals 0.2, and then we go through and follow the exact same steps as we did last time. So I'll give you a second just to go through and find the answers to that. If you've done that one, then I'm just going to move this down and show you the next one. And we have to do something slightly different for the next one, as you said before. So if you know what you're doing, feel free to go onto it and you can check your answers afterwards. Otherwise, we'll go through it in about half a minute's time. So this first question, we should have got x equals 11.53 ... as our first value, and then our second value was 168.4 ... So minor unrounded. In a question, it would either specify what to give it to, or generally you can give it to 3 significant figures. Okay. Question 2. Now we have to do this step 1 we talked about here earlier, because we're not dealing with x anymore, we're dealing with cos 2x. So what we need to do is adjust our range to make it between 0 and 720, and we're going to have 2x. So we had the range of 0 and x before, now we're going to have the range of 2x between 0 and 720. Then we can still go through and solve as normal. The only difference is we're not going to get answers for x straight away, we're going to get answers for 2x. So I'll give you some time to go through and get those first, and we apply our rules of symmetry to those first set of values. So I'll give you some time just to get this first value done. So we should get that 2x is equal to 60 degrees for our first value. And then we want to have our graph for cos between 0 and 720. So this is going to be two full cycles of cos. So we've got a value here and here, and then this is our first cycle, and then we've got another value here and here. And we can see that these second values in the second cycle are just 360 degrees plus the first values, because it's the second cycle, right? Because it's an extra cycle. So use symmetry to work out this value here, and then the cycle, the repetition of cos, to work out these values. So this is going to be this plus 360 will give us this one. This plus 360 will give us this one here. So the first value we get through symmetry is 300. And then we're also going to get 420 degrees and 660 degrees. Again, this is where we had an extra step in. So we added an extra step initially by doing it between 0 and 720. But we worked out 2x and we want values for x. So we now go through and halve these values and we say, well, therefore, x is equal to 30, 150, let me zoom out a little bit, 30, 150, 210 and 330 degrees. So these are our solutions. Any solutions, if we keep repeating this pattern, the other solutions will end up above 720, so they're not valid and we don't worry about them. Okay, so I'm just going to go ahead and review questions 3 and 4 and 5. And I'm going to give you some time to go through them before we go through them together. Again, be careful with tan. Here we need to adjust the range. For question 4, we'll have to use an identity. So now, again, like we said, we're starting to see those different elements come together now in this part of trigonometry. So I'm just going to start working through the solution for question 3 here. Again, most important part is that we adjust our range here. So our first value for this tan one should be 41.98 and so on and so on. And we know that for tan, it's just a simple matter of adding or subtracting 180 each time. Our range is between 45 and 405. So actually what we see is 41.98 isn't valid within our range here, because it's below 45 and our angle must be greater than 45. So it's helpful for us to find other values, but actually this value doesn't count as a solution because it doesn't fall within our range. And this is really important. If we hadn't adjusted the range here, if we had left this as 0, then we would have mistakenly included this in the range and said that this is a solution. So adjusting the range helps us, and this is a perfect example of why, because if we hadn't adjusted the range, we wouldn't have got this value. But we can now use this to find the other values that are solutions. So our next value is going to be 221.98 ... That is in the range, so we do include that. Next value, 401. And again, this is in the range. This is in the range this time because it's been adjusted. Previously, we'd gone up to 360, so we would have missed out this value. So there would have been two solutions actually we would have got incorrect here because we would have missed out this one and incorrectly used this one. So this is why adjusting the range is so important. Now we go through, because these are solutions to x plus 45, and we want solutions to just x. So we're going to get 176.98 ... degrees. I haven't rounded it, but the question would give you what value you want to round it to normally. And 356.98 degrees. So that's the answer there for question 3. And then I'll give you a little bit more time before we go through the answers to questions 4 and 5. Okay, so question 4, we need to use an identity before we can solve this, because we've got two different functions. We've got sine and cos. We can't use two different functions within the same question. But if we divide through both sides by cos x, we're just going to cancel on the right hand side. So on the right hand side we're just left with root 3. Then on the left we'd end up with sine x divided by cos x, which we know is just tan x. Right, which we know is just tan x. And then from there this becomes a fairly straightforward question. We don't have to adjust the range or anything else. We just solve for x. We get our first value as 60. And then our next value is 240, and these would be the only solutions between 0 and 360. And then this last one, question 5. So we've got 3 sine squared x plus sine x equals 0. So we can see here, hopefully, that we've got this. This looks like a quadratic. Anytime we see a squared, we should be thinking about a quadratic. And what we could say is, well, let sine x equal y, which means we can rewrite this equation like this. And hopefully now it's much more easier to see that this is a quadratic. And we solve it in the exact same way as we would a quadratic. So let's factor out the y. And then we can see we get two solutions. We get y equals 0 and y is equal to minus 1/3. If y is equal to those two things and y is equal to sine x, then sine x must also be equal to those two things. And then again we go through and solve the values just like we normally would for the two separate solutions. So this first one we would get x is equal to 0, 180 and 360. And then for this one our initial value would be minus 19.47, which obviously we don't include, but we can then use that along with the graph to work out the remaining values. I'm not going to draw the graph out for this particular question, just because we've done that many times before. But we should get at that using symmetry. We're going to get one answer of 199.47 degrees. And 340.52 degrees, rounded to an appropriate value. Okay, so hopefully you can see that within the 5 questions here, I can fit it into the full screen. Within the 5 questions here, we've covered quite a large range of methods of solving equations and different things that we can be asked to do. So first some basic rearranging, then we've got 2 questions that involve adjusting the range, then we've got a question that involves using an identity, and then lastly a question that involves us recognizing quadratic equations when they're written in a different format before solving. But the common theme through all of them is the idea of using the symmetry to get the other values, finding this primary value here and then using the symmetry and the graphs to get the remaining values. So it's really important that we have a solid understanding of how to use those graphs, and we know the key values on them as well. So if there's something you need to work on, just get into the habit of sketching out the graphs and marking on the key values. At which points did the graph cross our x-axis? At which point do our graphs have maximum and minimum? What are those maximum and minimums? Just to help develop that fluency, which then makes the rest of these questions a lot easier. Okay, so we've got a couple more slides to go with some exam questions on there. So I'll give you some time to read through that question and have a go at answering it before I put up the solution. And I will also reveal question 2 in a moment, in case you get onto that as well. I'm going to go ahead and reveal question 2 now, in case you have got onto that one, and then I'll give you still a few more moments before we go through the top question there. Okay, so I'm gonna just start going through question 1 now. We should have had, if you have finished question 1, we should have 5 solutions in total for question 1. So I'm just gonna go through them. Like we said, we can't have 2 different functions here and solve them in this manner. So what we want to do is change tan, use our knowledge of identity to change tan and rewrite this as sine theta over cos theta is equal to 2 sine theta. And now we've still got two sets of different functions because we've got cos theta in here as well. But all of the terms in the equation have sine theta involved. And again, that's a hint. If we go back to the previous page, we had all of the terms here having sine theta. This is again a similar idea. What we want to not do, and what is a really common thing to do at this point, is to divide through by sine theta. If we were to divide through by sine theta, this would cancel and we would get 1 over cos theta equals 2, which we can then rearrange. But we miss out on some solutions in doing that. Instead, what we want to do is exactly the same thing we did last time we had the quadratic that we were dealing with, is to get this into a format where we can factorize it. So first, let's take everything over to one side, and then let's factor out sine theta. So we've got that solution we mentioned earlier of 1 over cos theta being equal to 2, but we've now also got this solution of sine theta being equal to 0 as well. And it's really important that we have both of those. So we get sine theta equals 0 and cos theta equals a half. Then we go through and find theta for those respectively, and we should get that theta is equal to 0, 180 and 360, and these are the solutions from sine theta equals 0, and also 60 and 300, and these are the solutions from cos theta equals a half. So if we just used the cos theta, we would have missed out 3 solutions, in fact the majority of the solutions here. So I'll give you a few more minutes before going through the second question there. Again, this time the question is prompting you to use the identity before you go through and solve this one. Really good question. So let's go through this bit. So from this bracket here, we get that 1 over cos theta minus 2 equals 0. So if we rearrange, we get 1 over cos theta equals 2. And then if we take reciprocals of both sides, we'll get cos theta is equal to 1 over 2. And that's where that comes from. Okay? So let me know if that makes sense. So just like when we're solving quadratics, yeah, we say each bracket equals 0. That's how we get this first statement here. So saying, well, either this bit equals 0 or this bit equals 0. And in order for this bit to equal to 0, cos theta must be equal to 1/2. Okay, and then we're just rearranging to solve. You're welcome, Breathe, no worries. So, the next bit here we need to do some rearranging first. So we're going to use our identity. We get, well, this is then equal to 4 1 minus sine squared theta. So I've substituted our identity into here. What we're saying is, well, if sine squared plus cos squared is equal to 1, then cos squared is equal to 1 minus sine squared. So that's what we've done, substitute this bit into here. Then we're going to go through and expand this bracket. And we're close to this kind of format now. That is asking us to show that in. So now it's just about rearranging this question and saying, well, we can go straight from, well, therefore we get 4 sine squared theta plus sine theta minus 3 equals 0. And we get the first part of that question. Then we can do what we did last time we had a quadratic. And we say, well, let sine theta equal y. So we get 4y squared plus y minus 3 equals 0, which gives us a quadratic. And then we need to go through and solve this, and you can use your calculators to solve it, or just attempt some trial and error to solve it there. But we should end up with it factorized as 4y minus 3y plus 1 equals 0. So therefore y is equal to minus 1 and y is equal to positive 3/4. And like we said, if sine theta is equal to y, then we can say, well, therefore sine theta equals minus 1 and sine theta equals 3/4. And then we go through and solve and get our values as normal. And what we should get here is that you get theta equals minus 90, which is clearly not within our range, so you can ignore it, but it's helpful. We need to know that in order to get our other values, which would in this case be 270 degrees. And then from this bit of sine theta is equal to 3/4, we get theta is equal to 48.5 and also 131.4. And we round those two appropriately. So we've got 3 solutions here for this question. So again, I'll give you a moment just to get anything you need to get copied out, or any corrections you need to make. And then we've got one more exam question for today, and then we are done. And again, hopefully you're seeing those links of we've combined the identities, the use of trig graphs, and the use of solving equations, the use of quadratics, all in both of these questions. So I haven't drawn out the graphs for these questions just because some of these values are fairly straightforward. We should always be making sure we're drawing out the graphs and using them as well. Okay, so last question for today then. I'll give you some time to have a go at this and get it copied out before we go through it together. Okay, another couple minutes and then I'll start going through the solution for this. Okay, so I'm just going to start talking through part A for now. So we can see the question is explicitly asking us to give it in the form of tan. And we said earlier, normally we want to try and get rid of tan and simplify things down into sine and cos. In this case, the question is explicitly asking us to not do that. So we're going to go ahead and do that. But we still want to use this idea of sine x over cos x equal to tan x. And we can see that actually what we want to ask ourselves is how can we make any of these terms look like this? So if we divide by cos x, we'll get sine over cos x here. This will cancel out, and this will also cancel out as well. So what we end up with is, if I write out the original equation, just so it's really clear, so we get sine x minus cos x is equal to 6 cos over tan x. So we want to divide through everything by cos x. And we said we get sine x over cos x, which will give us tan x, minus cos x divided by cos x will give us 1. And again, cos x divided by cos x here will just cancel. So these two cancel. So we're just left with 6 over tan x. Now we've got no other trigonometric functions. We've only got tan. So we're much closer to this format than we were to start off with. And actually, there's only a couple more steps involved. From here, all we need to do is multiply through both sides by tan x, because that will remove it from this denominator here. And we end up with tan squared x minus tan x is equal to 6. And then one last step is to take the 6 over to the other side. We get tan squared x minus tan x minus 6 equals 0. And that's the first part of that question, part A, done. And then part B, it says solve, and it's given it in the sine and cos and tan format. But actually, we can go straight to this. And what we're trying to say is, well, we know that these two things are equal. So we're going to solve for this instead. And again, we can say let tan x equal y. Therefore, we get y squared minus y minus 6 equals 0. And factorising, we're going to get y minus 3, y plus 2 equals 0. Therefore, y is equal to 3 and y is equal to negative 2. And then we get, therefore, tan x equals 3 and tan x equals negative 2. And we can go through and solve and find those values of x within our range here. So we should get here 71.5 degrees and 251.5 degrees. Again, these are unrounded values. And for the right hand side, the first value we get is minus 63.4. Obviously we don't include that because it's not in the range. However, we still need to use that to find the next set of values. Sorry, that should be 116.5. And 296.5 as well. So we get our 4 solutions for x there. Okay. And again, hopefully you've seen that we've gone through several different steps. We've used identities here, we've used quadratics, we've solved it here, we have used the graphs here to find the rules of the graph and the symmetry of the graph here to find these extra values. Again, in the interest of time, I haven't drawn out the graphs, but we can go back and draw them now to see how they would have worked. So we had an initial value of 71.5 here for 3. And this is, like I said, tan repeats every 180, so we would have got those 2 values there. And then we had the first value for minus 2 was in fact here somewhere. And again, we just added 180 to get the value here, added 180 to that to get the value there as well. Okay. So always draw these graphs out so we can see these rules take place and how they work, the rules of symmetry. And that's it for week 7. So just a quick summary of what we looked at today. Some key points and things to look out for when solving trigonometric equations, when proving identities and manipulating identities. Like we said here, always draw a sketch or a graph and annotate, going back to the questions on sine rule, cosine rule, and the area of a triangle, and making the diagram fit what we need it to fit, rather than always relying on the diagram as it's given to us. Okay. So next week we're going to be looking at logarithms and exponentials. In the meantime, stay safe and take care. Get in touch with us on Twitter and Facebook if you've got any questions. Go back and watch any of the video that you need to watch. And we will see you next week. Take care.